In this lab, we want to use the natural response of a second-order mechanical system to identify model parameters, the damping ratio, and the natural frequency for the system. We'll use those parameters to design a filter and then build an overall state variable model for the third-order system, correlate that with our data. This is a homogeneous differential equation. The right-hand side is 0. For an underdamped system, the response is going to look something like this blue line. It'll oscillate and decay. The decay rate is exponential, and it'll be of the form y0, which is the initial condition on position, e to the minus damping ratio omega n times time. Notice a couple of things about this. As time goes to infinity, the value of y of t has to go to 0. Also, Td, which is the damped period, the time between two successive peaks on this curve, is 2 pi over omega sub d, where this is the damped natural frequency. So if we measure this time period, we can determine omega sub d for a lightly damped system. So if squiggle is considerably less than 1, then omega sub n is approximately equal to omega sub d, because omega sub d is omega n times the square root of 1 minus squiggle squared. To get a damping ratio, squiggle here, we can use these values, y1 and y2, at successive peaks. And the ratio between the two, y2 over y1, is going to be e to the minus squiggle omega n times the difference in time. If we use one time period, that becomes t sub d. We can solve this equation for squiggle, or the damping ratio, by taking the natural log of both sides. So this side becomes the natural log of y2 over y1 is equal to this, negative squiggle omega n t sub d. And if we take this expression here and plug it in there, we can get an expression for the damping ratio in terms of these two y values. Now let's measure this natural response and work with it to get these values. This is my mechanical system. I've got a spring with a platform on the bottom of it. There's an acoustic proximity sensor here to measure the position of the bottom of the spring. To get the natural response, I apply a set of initial conditions by displacing the platform and releasing it. Now I'm going to measure the response of this as a function of time. Let's take a look at that data and analyze it. The first thing I want to do in this lab is determine the sensitivity of the acoustic proximity sensor. In order to make the sensor work, I need to provide power. So I don't need the negative power supply, but I am going to use the positive power supply to apply 5 volts to the sensor. And I'll turn on power. Now if I go to the logger or meters instrument, I only need channel 1 DC. So at the current position of my platform, I have about 135 millivolts of output voltage. I'm going to move the platform down by about 10 inches. That'll give me a new value for this. The difference between those two values divided by the distance that I move it is going to be my sensitivity in volts per inch. So record those two values, do the math, and you're done with this part. Now I'm going to measure the natural response of my system. I've already got power applied from when I measured the sensitivity, so let's go open up the scope instrument. I'll get rid of channel 2 because I'm only going to measure one thing. Make this a little bit more sensitive, and this system is going to respond really slowly, so I'm going to pick 6 seconds per division. Start acquiring data. And stretch the spring and release it. Now I'm going to want to trigger this to get my data. I'm going to choose a trigger level associated with a rising edge at about 150 millivolts. So I'm going to use a normal trigger. It's going to be a rising edge, and it's going to be 0.15 volts. Now, when I get my actual data, I'm going to use a single sequence acquisition. Notice that the trigger is configuring. That will take a while because of the long time base expansion. Now the trigger's armed and we're ready to go. I'm going to stretch the spring, release it. The system triggered. Now we're acquiring data, which will take a while again because of the 6 second per division time base. There's my data. I'm going to expand it a little bit. 2 seconds per division. Go over there. Now I need two things. I need a damped time period. I'm going to use cursors to get that. There's my first cursor. So the amount of time required for one period of data. So now I can find a difference. So the difference is about 1.2 seconds. So that can give me my damped natural frequency. Now I need a damping ratio. So I need to get the value of the function at 2 successive points. In order to get a little bit better response, I think I'll go 3, 4, 5 periods. Averaging across 5 periods will probably give me a slightly better estimate of the damping ratio. So there's my first value. So Y1 is 202.86 millivolts. Y2 is 176.19 millivolts. I can use those two values to get a damping ratio, but I also need a DC offset. This value here, which I'll use that for, should be my zero. It's the offset. So that value is 149.52 millivolts. I need all of those pieces of information. Now we want to design a non-inverting low-pass filter to process the data. Our output data from our acoustic proximity sensor is fairly noisy and has low sensitivity. We can use this first-order low-pass filter to get rid of some of the high-frequency noise and to increase the sensitivity at DC. The frequency response of this circuit is shown here. As omega goes to 0, the DC gain, this term here, just goes away. The DC gain becomes R1 plus R2 over R1. If you apply a definition of the corner frequency of this circuit is 1 over R3 times C. So we want to set the corner frequency of this circuit to be about 10 times the damped natural frequency that we measured earlier. And we want a DC gain that corresponds to the desired sensitivity over the measured sensitivity. So the sensitivity we have without the filter. So we know what we want omega sub c to be. We know what we want this number to be. These correspond to two equations with 4 unknowns. So we'll have to arbitrarily pick a couple of values. We'll have to pick either R3 or C for this equation. And we'll have to pick either R1 or R2 for this equation and then solve for the parameter that we want. I've designed my filter to have a DC gain of about 10 and a corner frequency of about 7 Hertz. Now I can test this by applying individual sinusoids at various frequencies and measuring the magnitude of the input and the magnitude of the output. But I think I'll use the network analyzer for this. This is a fairly low frequency, so I'm going to use a starting frequency of 1 hertz and a stopping frequency of 100 hertz. I don't want this to take forever, so I'm going to only use 20 samples. The DC gain of 10 means that I can't have a very high input voltage. And I'm going to start out at 40 dB and have a range of 40 dB. My filter's active, so I need to apply power to this, so plus minus 5 volts. Turn power on and start scanning. Now, because of the really low frequencies involved, this is going to take a long time. I'm going to go have a cup of coffee and come back later. Okay, there we go. I've got a DC gain of about 21 decibels. 20 dB would be 20 times the log 10 of 10, so I've got just about my gain of 10. The corner frequency is where the gain is down by 3 decibels. So here at about 17 is where my corner frequency would be. It's looking like it's about 7 or 8 hertz, which is good. So it looks like my filter's doing what it's supposed to do. Now I've got my filter implemented. I'm going to use channel 2 to measure the response out of the filter. The filter requires positive and negative power supplies, so I need to turn this on, and that will be negative 5 volts. Power is still on. Now let's do another single sequence acquisition. Stretch the spring again and release it. There's my filter data. It's got a much higher amplitude and it's considerably smoother than the unfiltered data. Now I need to export the data for later post-processing. So, File, Export. I don't need comments or headers. And I want the source to be the scope. I'll save that to a text file. And spring mass damper will be the file name. Save that. Now we can go to Matlab and analyze the data. The model of our system is going to be in terms of the output voltage from the sensor V sub H with a hat over it. The acoustic proximity sensor puts out a voltage. But that consists of an offset V sub H bar plus V sub H hat of T. We need to get rid of this from our data and just write our differential equation in terms of V sub H hat, where V sub H hat goes to 0 as T goes to infinity. So, picking states for this equation, my states are always the result of an integration. If I take this highest order term and integrate it, I can get my first state is the derivative of V sub H hat of T with respect to time. Then if I integrate that, that gives me my second state, which is just V sub H hat of T. So the derivative of x1 dot is the second derivative of V sub H hat of T with respect to time. And the derivative of x2 is just this derivative, which is x1. I can solve this equation for the second derivative of V sub H, and that will give me this equation, and this is my second state equation. Now let's come up with a state space model for our first order low pass filter. Here's our filter. Our input is going to be the voltage out of the sensor, which has just already been defined as our state x2. We have one energy storage element. I'll usually define my states as being voltages across capacitors and currents through inductors, so my state x3 will be the capacitor voltage. If that's X3, the capacitor current is CX3 dot. Applying the op-amp rules, if this voltage is X3, then this voltage is also X3. Now if I call this node A and this node B, and write KCL at A, this current plus this current is equal to 0 at A, so X3 minus X2 over R3 plus the current through the capacitor, which is just CX3 dot, is equal to 0. And then KCL at B, this current through R1 plus this current through R2 is equal to 0. So X3 minus 0 over R1, the current through resistor R1 leaving node B, plus X3 minus V out, which this is the output voltage from the filter, over R2 is equal to 0. So this equation here will give me my state equation for X3, and this equation here will provide my output equation. So this equation here plus my previous two state equations for the mechanical system will give me my state variable equations, and this will provide the output equation I need, and I can simulate the response in Matlab. Now I'm going to use Matlab to simulate the system response and correlate that response to the data. So I'm going to put my work in a script file, and I'll call that natresp demo. First thing I'm going to do is set up my nominal initial conditions. So Q, the output voltage from the filter, I'm going to claim is 1.67. The original output voltage from the sensor is 0.148, and the initial time is 0.28. None of these numbers correspond necessarily to anything that's in the previous data file that I showed you. Next, I'll set up my damping ratio, my initial estimate, my natural frequency, and the output initial conditions for the sensor. So the initial sensor voltage is this, the rate of change of voltage with respect to time is 0. Then I'll use those initial conditions along with the initial voltage out of the sensor for my initial conditions for the third order system. Now I'll load my data file. It's a text file, so I use the -ASCII specifier. I'm going to extract the time data, which is the first column minus the initial time, so that the initial condition corresponds to t equals 0. And the output data is the third column, the filtered data, minus the offset, Q underscore filter. Now I'll set values for resistances and capacitances for the filter, my A, B, C, and D matrices, the final value for my simulation, and create my state variable model called sys. Finally, I'll use the initial command to calculate the response to a set of initial conditions, save those values, and I'll plot the simulated response versus the expected response. So let's run the file. The blue line is my simulation, the red line is my data. It looks like my damping ratio is a little too high. So I'm going to go back in and change this. That's one of the main reasons to have this in an M file so that I can change it easily. Change the damping ratio to 0.01. Looks pretty good, but it's not damping out quite quickly enough for my liking. The response is more or less gone out here after 40 seconds. So let's split the difference and call this 0.012. That actually looks pretty good. I can have a pretty good feeling that I've got the right model for the system now.